Now we're going to look at what we call the numerical derivative of a function. So for small values of h, the difference quotient, f of a plus h minus f of a over h, is a good numerical approximation of the derivative of our function at a. The symmetric difference quotient, f of a plus h minus f of a minus h over 2h, will produce an even better approximation of our derivative of our function at a. So we call this our numerical derivative of our function. Symbolically, we can write NDER of f of x, or NDER, and sometimes we put f of x and that value of a that we care about when we really want to emphasize both the function and that point. In most of the cases that we're going to look at, a small h value of 0.001 is going to be more than enough to give us an accurate approximation of the derivative of our function. So if we want to find the numerical derivative of the function f of x equals 4x minus x squared at x equals 3, we're going to use h equals 0.001, and we want to know, is the function differentiable at x equals 3? We're looking for the numerical derivative NDER of our function here is 4x minus x squared, and the point that we care about is where x equals 3. So in some of your calculators, your handheld calculators that many of you probably don't have, this is how you would actually enter it in. There'd be a numerical derivative button, and then you'd write in your function and a comma and a 3, and then hit enter, and your calculator does all the work for you. But we can also calculate this by hand. We know that we'd look at the function at a plus h. So here that would be our function at our a value is 3 plus our h value is 0.001 minus the value of our function at a minus h. So minus the value of our function at 3 minus 0.001 over 2 times h, so 2 times 0.001. So this means that we're really looking for the value of our function at 3.001 minus the value of our function at 2.999 over 0.002. We actually figure out what the values of our function are at those x values. So if we plugged in 3.001 into our function in place of x, we'd have 4 times 3.001 minus 3.001 squared. And we're going to subtract from that. I'm going to put that in brackets just so we know that that's one of our functions. We're going to subtract from that 4 times 2.999 minus 2.999 squared. And the whole thing is divided by 0.002. And then we just plug that into our calculator and we should get out -2. So here we have a y value that we get out of this. So yeah, our function's differentiable at x equals 3. And if we want to verify this, we can actually look at our function. We can go to the graph of our function, f of x equals 4x minus x squared. We can see this nice quadratic, this parabola. If we look where x is equal to 3, x equals 3, we're at this point on our function. Yeah, we're definitely differentiable there. It's a nice, smooth, continuous function. We're differentiable everywhere on it. And remember, putting that calculation into Desmos, you can do even with the brackets. You could say 4 times 3.001 minus 3.001 squared minus 4 times 2.999 minus 2.999 squared. Go down there. And then put the whole thing That's going to make me put all that in parentheses, isn't it? Desmos might prefer parentheses here, but let's see, 0.002. Yeah, Desmos would prefer these to be parentheses, doesn't want brackets. So if you change those to parentheses to make Desmos happy, there you go. There you can see that you get that -2 out for your numerical derivative. So you can always use Desmos for your calculations here for things like this. So let's try one more. We want to find the numerical derivative of the function f of x equals the absolute value of x minus 3 at x equals 3. And we want to do the same h value. We're going to use h as 0.001, and we want to know, is this function differentiable at x equals 3? So we're looking for the numerical derivative of our function, the absolute value of x minus 3, and the x value we care about is when x is 3. So we're going to take the value of our function at 3 plus our h value, 0.001, minus the value of our function at 3 minus our h value, 0.001, and divide that all by 2 times our h value, 0.001. Which means we want the value of our function at 3.001 minus the value of our function at 2.999, all divided by 0.002. So the value of our function at 3.001, we take our function, the absolute value of x minus 3, so this would be 3.001 minus 3, all in absolute value, minus the value of our function at 2.999, we'd have the absolute value of 2.999 minus 3, and the whole thing is over 0.002. And if you go into Desmos, you can do that calculation if you are feeling super lazy and don't want to do it in your head. So we can do the absolute value of 3.001 minus 3 minus the absolute value of 2.999 minus 3. Close my absolute value, close parentheses, over 0.002, and we see that we get 0. Is 0 a number? Yeah. So our numerical derivative is 0. We think that the slope of our line there is 0. We always want to verify this with our graph though, because if we look at our function, f of x, or y equals the absolute value of x minus 3, it looks like this. And where x is 3, we see that we have a corner, a nice sharp point. So we're not actually differentiable there. So just because our numerical derivative calculation gives us a number, that doesn't mean that we're actually differentiable there. You always want to verify with your graph. You always want to look and see. If we come to a corner or a cusp, or we have a jump discontinuity, or any of those things that we talked about at the beginning of this lesson, we know that we're not actually differentiable there. So the numerical derivative calculation can throw you off. It can give you numbers that aren't actually true, that tell us that we're differentiable where we're not actually differentiable. Then a couple of important theorems that we have. We're not going to go into detail on them, but just some things that you should know about. Differentiability implies continuity. If our function has a derivative at x equals a, then our function is continuous at x equals a. The converse of this theorem, however, is false. Hopefully you talked about converse statements back in geometry. So we've seen examples of functions that are continuous at a point but not differentiable at this point. This function, for example, continuous at x equals 3, not differentiable at x equals 3. And then the other theorem that you need to know about is the intermediate value theorem for derivatives, which says that if a and b are any 2 points in an interval on which f is differentiable, then f prime takes on every value between f prime of a and f prime of b. So the derivative of our function takes on every value between the derivative of our function at a and the derivative of our function at b. We've looked at the intermediate value theorem. This is just saying it works the same way for our derivatives.